Since their invention in the late 1950s, these building blocks of the electronic world have become so small and so sophisticated they can control an airplane, yet take up no more space than a few grains of sand. And incredibly, that's where it all begins: sand. Sand, also known as silicon dioxide, contains silicon, the second most abundant element on Earth. Almost all integrated circuits are made from silicon. But how do we get from this to this? Early designs for integrated circuits were hand-drawn. An engineer drew a circuit using symbols for each component. Stencil-like patterns were made from the drawing. The design was carefully checked, reduced optically onto photographic glass plates, called photomasks, then printed onto a silicon wafer using a process called photolithography. Today, circuits are designed by sophisticated computer-aided design systems.
You start off with a crystal seed, and then you very, very slowly withdraw this seed from a melt. And that's to create an even size ingot.
Now the ingot is sliced in order to be a preset, exactly measured thickness.
And then you polish it. And it's polished to a finish that is flatter than a telescope mirror.
The polished wafer is placed on a furnace containing highly heated pure oxygen, where it grows an insulating layer called oxide.
That oxide has the wonderful property that on silicon it's impervious.
A glass photomask with the pattern is created from the design. The pattern is printed onto a layer of resist on top of the oxide, much like a pattern is silk-screened onto a t-shirt. Windows are etched through the oxide, exposing select regions of silicon below.
The places where it exposes the light, it will solidify or cross-link, and then you put it into another solution, which is the developer, and it dissolves away the places that were not exposed to the light.
Dopants, which are elements that change the electrical properties of the silicon, are now introduced.
These dopants, when introduced, will impinge on the silicon, and these paths will be the paths that become electrically activated that form the device itself.
At this point, the wafer holds isolated microelectronic components.
Now we have a wafer which has integrated circuits diffused into its body.
So to hook them together, you now start to apply the metallization.
But now it's all connected by a single sheet of aluminum.
Then you would etch away the unwanted metal. And then you have these contacts that allow you to hook up to specific devices.
The chips are now tested.
We devised testers which had probe needles that could be inserted into an electrical tester and then drop down on the device, one probe per each little contact point made on the device.
If it doesn't pass the standards of the test program, then you put a little dot of ink on it. When you cut it up, you can pick out the ones with the ink on them and throw them away.
Good chips are mounted in protective packages. Thin wires are attached to the exposed metal pads to make contact with the outside world, and packaged in a variety of forms for different uses. Today, more than 1 billion transistors can be packed on a chip the size of a thumbnail.
And this all comes as a result of shrinking the size of each individual component.
The tested chips, packed with integrated circuits, are placed in devices we use every day. We press a button, move a mouse, tap a key, touch a screen, and our devices respond, thanks to the integrated circuits inside. Thanks to the people who invent, design, and build them. And thanks to a common substance with uncommon potential.